Good. So you guys are all probably going to take some oath at the end of this that you're going to try not to hurt your patients, even the really whiny ones, right? So the concept is first, do no harm. And I actually was really disappointed because I Googled the other day that you guys don't actually say that, which is really kind of a crushing blow to the Hippocratic Oath for me. I think you should all whisper it like under your breath anyway. But B cells kind of say that. They take this oath to not do harm, all right? But unfortunately, sometimes they fail. And that's part of what we're going to talk about next hour is autoimmunity. And by that I mean autoreactive or self-reactive cells. These are cells or receptors that respond to your own tissue. And self-antigens, these are the antigens, like the actual component that the cells are responding to, okay? All right, so this process is mediated by a process known as selection. So we have B cell selection and we have T cell selection, okay? All right, so with B cell selection, we have a couple options. So let's say we're a B cell, and we're feeling pretty cool because we rearranged all our receptors, we're expressing IgM. We're floating around the bone marrow, talking to all our friends, trying to get some sort of survival signal. Except in the bone marrow, the only thing really expressed to show if you're ready to go are self-antigens. You're hoping not to respond here. If you do not make a response to a self-antigen, you actually get cued to class switch. So class switching happens to allow for dual expression of IgM and IgD on the cell surface. So if IgM is like your learner's permit, so you're like cleared to drive with your friend that's 18 and way cooler than you, IgD is your driver's license. This is what is going to let you leave, get in the car and go, okay? So IgD, you get class switching, you get expression of IgD. Now you can leave the bone marrow and go out to the spleen or the lymph nodes where you'll actually encounter real antigen, right? So Dr. Lint was talking about how the cell is just hanging out going, oh man, I'm getting old. I really, really hope I see some antigen soon. Then it gets antigen and it gets a survival signal. That happens after they've expressed IgD and left, okay? All right, unfortunately, we're gonna have some self-reactive antigens because we did this with a completely random process using materials that are similar to the materials we're trying to protect against, right? So if this happens, if you get cross-linking, you get told to stay in the bone marrow. And then you have some options. So one, we can go back and rearrange our light chain. So let's say the first time you rearranged, you were able to make a functional, and that means heavy chain binding light chain, on the first or second try. So you still have tons of genetic material. So you get induced to rearrange your light chain again, thus creating a brand new IgM kappa maybe. Now let's say you go to do that test again and you get really strongly stimulated, you get killed. Really, really strong stimulus leads to clonal deletion. You're too strong, we can't fix you, we can't remediate you, you're done. Or you might get to go through it again. So you can keep going through this until you run out of information, right? Or maybe you made a good one and now you're gonna get signaled to make IgD and leave. So one of three things: death, receptor editing, get released. And receptor editing is pretty much always an option until you run out of genetic material. When you run out of J chains on all 4 of your chromosomes, now it's do or die time. You either have a functional non-self-reacting BCR or you don't. The end, okay? Now, this process works really, really well for soluble, multivalent, ubiquitously expressed antigens throughout the body. Okay, like you're not going to make antibodies to your epithelial cells, even though there's proteins all over that. So that's the kind of thing that it'll work really, really great for. It does not work well for low expressed or monovalent proteins. Then something, or lipids or whatever, then something else happens. So in this case, you have a multivalent self molecule. You're either going to get clonal deletion or receptor editing, and eventually it either dies or comes out as a non-autoreactive cell. The other option is a process known as anergy, So energy is like you're ready to go, you're feeling good. Energy is like you're a zombie. Like you're not responding. I liken it to, I have a 3-year-old, and occasionally, very rarely, I have to use the TV as a babysitter, right? My 3-year-old is obsessed with pirates. So if I put on Jake and the Neverland Pirates, something produced by the evil Disney Corporation to torture parents, I could, like, if I was a bad parent, throw things at my 3-year-old's head and he would not respond. He would just, that's it. All that exists in his world is Jake and Captain Hook. So that's kind of what energy is. Energy is, it's a catatonic state. There is no breaking through it. And what happens to these energized cells is they get released out into the periphery, and since they're not getting any survival signals, they'll die. So a activated or a functional B cell, I won't say activated, a functional B cell that gets released into the periphery, that's gonna live for a couple of weeks. Unless it gets stimulation, then it'll live longer, right? An energized B cell, 1 to 5 days, not very long, okay? Good. So you